Let us continue to work with the penguins dataset and understanding how one can use graphing or plots to perform exploratory data analysis to gain insight into any dataset. As a first step, let us load the Palmer Penguins and ggplot2 libraries by running this code chunk. And the first thing I'd like to discuss is a more concise form of calling ggplot. So recall that when we call ggplot, we have the function name and open parentheses, and the first argument is data, and the way we specify it is we give the argument name equals, and then we give the data set, which in this case is a data frame. And the second argument is the mapping, which maps columns in the data frame to aesthetics, visual properties of the graph. So in this case, we are mapping the flipper length column to the x-axis and the body mass to the y-axis. And then we use the plus symbol and a geom function which specifies a geometrical object with which the data are plotted. So in this case, we are using the geom point function, which will plot the data as points. And I can execute this code chunk, and this creates the plot that we did in the previous lecture on the penguins dataset. Now, it's possible to write this code in a more concise fashion by omitting the names of the argument. So we can leave out the name of the argument. The main thing to be careful when we are writing the function in this concise way is that we should not change the order of the arguments. So in ggplot, the data argument is the first argument and the mapping argument is the second argument. And if you change this order, if you're specifying the name of the argument as it's done above, then the order doesn't matter. You can exchange them and the code will still work. On the other hand, if you are writing more concise code by omitting the argument name, then the order must be observed. In this case, the data has to be the first argument and mapping has to be the second argument. As a reminder, if you would like to know what is the order of the arguments in any particular function, then you can go into the console over here and question mark the name of the function, and it shows you the list that match the names, and you can use return and the arrow keys to select it. And then when you hit return here, it will show you the help for that function. In this case, it's showing us the help for ggplot, and it shows what are the arguments that ggplot takes, and the order of the argument is the same as the order in which the arguments are presented in the help page. Okay, so let's go back to the study guide, and now let's talk about visualizing distributions of a single variable. And one of the first steps in data analysis is to understand what is the probability distribution of a random variable. In the penguin dataset, we have the species variable, and it takes three values: Adelie, Chinstrap, and Gentoo. And as we discussed before, this is a categorical variable or a factor variable since it only takes a finite number, a discrete number of values. And we would like to visualize the distribution of these three different species So we would like to know what is the frequency at which Adelie, chinstrap, and gentoo penguins occur in these islands. And we can do that with ggplot. And of course, the first argument is our dataset. So we will use penguins. The second argument is our aesthetic mappings. And note, I'm not using the argument names here. So I'm using the concise notation. Now we need to map a column, in this case, the species column, to an axis. So let's map it to the X column. So we will say X is species. Um, Since we are only dealing with a single variable, we want to visualize the distribution or the frequencies of the species. There is no y mapping in this case, and the y mapping will be automatically calculated by ggplot to be the frequency of the occurrence of each species. And now we need an appropriate geom, and um, since we will have just three numbers, um, a good option here is the geom bar, geom function, which will make a bar plot, and geom bar will automatically compute the frequency of the species. And now I can run this code chunk, and now ggplot has created a bar plot of the frequencies. The count of the different species here. And this is the probability or the frequency distribution of the species. And we can see that Adelie are the most abundant and chinstrap are the least abundant of the species. Now, this was with visualizing the distribution of a categorical variable, but you could also want to visualize the distribution, the frequency distribution of a continuously varying numerical variable, and that is visualized as a histogram. For example, we may want to see what is the frequency distribution or the probability distribution of the body weight of the penguins. And let's go ahead and use ggplot to plot the histogram. And um, we will have to change the call to ggplot in two places. First of all, of course, we are not using the species variable or the species column, but the body mass g column. And the second is we will use geom histogram instead of geom bar. And geom histogram takes an argument called bins, and bin specifies how many bins should the range over which the body mass varies should be divided, so that the frequencies can be counted in those bins. And let's go ahead and try 30 bins and run this code chunk. And here we see the histogram, and you can infer a number of things about the distribution of the body mass of these penguins, um, such as, well, the most common, the mode of the distribution is around 3,500 grams. And you should try and infer as many things about how body mass varies among these penguins as you can. Now, what if you keep increasing the number of bins, or in other words, you keep reducing the bin width? As you do so, you will discern more and more detail in this frequency distribution, and in the limit of the bin width going to zero, this histogram will approach what's known as the probability density function. And you can, in fact, visualize the density with the geom density geom. So let's go ahead and try and do that. I will first copy, um, our code chunk, paste it here, and now instead of geom histogram, I will use the geom density. And when I run this, I can see probability density. And if you compare it with the histogram, it seems to be a smoother version of the histogram in which we can see three peaks. And you should try and make sense of what having these three peaks, what's known as a trimodal distribution, can mean for the distribution of body mass in these penguins. So far, we've been talking about how we can understand the distribution of a single variable. Next, let's discuss how one can visualize relationships between two or more variables in order to get insight. And the approach appropriate for visualizing relationships depends upon what type of variables they are. So let's first consider the situation where we would like to understand the relationship between a numerical and a categorical variable. So, for instance, if we wanted to see what is the relationship between the body mass and the species of the penguins. One of the problems one could face when trying to visualize these distributions is the plots could get very busy. For instance, one could simply plot the actual values of the data points. And so you could visualize the distribution this way, where you can see that most of the values occur here in the lower part. Another way, of course, that we have looked at of visualizing distributions of a numerical variable is through histograms. But if we are going to be comparing these distributions across different values of the categorical variable, for instance, species, the plot could get very busy and hard to interpret. In such situations, it can be very useful to display information about the distribution, but to summarize it so that you're not showing all the information, the whole distribution. And one methodology type of plot to summarize distributions is known as the box plot. And what you do in the box plot is you plot the median. So that's the 50th percentile, and you can see this is the 50th percentile of the histogram, and you put a line there. Then you put the 75th percentile and the 25th percentile, and that forms the box. And so that's known as the interquartile range, and that forms the box. Any points more than 1.5 times the interquartile range beyond the box are considered outliers. So these 2 points, which are very far, more than 1.5 times the interquartile range away from the box, they're considered outliers and are plotted as individual points so you can see the outliers. And you draw whiskers up to the farthest non-outlier point. And so the whisker goes up until this point. There are no outliers on the lower end of the distribution. And a box plot such as this allows you to see several things about the distribution. It allows, for example, here to, of course, compare the medians and the percentiles, but you can also see here that this distribution is skewed where lower values are much more common and larger values, there's this long tail of the distribution, they're less likely, and you can see that in the skewness of the box where the median, it doesn't lie in the middle of the box but lies at the bottom. And therefore, box plots are a good way to visualize distributions without making the plot very busy. And so now let's go ahead and actually visualize the relationship between body mass and species for these penguins And I'm going to insert a code chunk. And now our data will still be, of course, the penguins data set, but the aesthetics on the x-axis, we will put the species, and on the y-axis, we will put body mass G, and then the geom we're going to use is the geom box plot. And we can run this code chunk, and we can see that it has put the species on the x-axis. So now we are looking at three different distributions of body mass, one for the Adelie penguins, one for the chinstrap, and the third one for the Gen 2 penguins. And now it's possible to compare these medians and also the 25th and 75th percentiles of these box plots to reach conclusions about how body mass, or to be more accurate, how the distribution of body mass differs between the species. And you should take a moment to analyze this plot and reach conclusions about body mass and how it differs between these species. Another approach to visualizing the relationship between a categorical and a numerical variable is to plot the density using geom density of the numerical variable and use color, map the categorical variable to the color aesthetic so that we can visualize multiple different densities all on the same plot. So in this case, what we will do is we will map the body mass, which is a numerical variable, onto the x-axis and map species to color, and then we will use geom density. And now when we run this code chunk, we can see that we have three different densities being plotted, one for each species. The Adley is in red, Chinstrap is in green, and Gen 2 is in blue. And in making plots like these, one of the aesthetic choices one could make is, instead of mapping the categorical variable onto color, we could map it onto the fill. We'll create filled densities, which looks nice, but it has the problem that you cannot see the Adley and Chinstrap distributions entirely, since the Gen 2 density is hiding them. In this case, we can use the aesthetic called alpha, which is a technical word for transparency. So we can give an aesthetic mapping in geom density for alpha being 0.5, which means it has 50% transparency, and alpha of 1 means completely opaque, and alpha of 0 means completely transparent. So now when I run this, you can see that the densities are filled, but they're transparent, semi-transparent, and therefore you can see the distributions which were previously being hidden by the Gen 2 distribution. What if we wanted to understand the relationship between two categorical variables? For example, if we wanted to understand how the population of the penguins is stratified on each island by species. And therefore, one could do this by mapping, let's say, island onto the x-axis and the species onto the fill aesthetic, and then using geom bar to make a bar plot. Now, when we run this, we see the island on the x-axis and the distribution of different species on each island as a stacked bar plot, and one can reach a number of conclusions about the species and its relationship distribution on these different islands, and you should try to reach as many conclusions as possible based on this plot. Next, you may want to visualize relationships between two numerical variables, and we have already done so. The one standard way of doing this is with scatter plots, and we had made a scatter plot between body mass and flipper length. So let's jump ahead to what happens or what one could be doing when you have more than two numerical variables. So, for example, we may want to understand the relationship between body mass and flipper length, how this relationship is affected by species and island. So we could have a total of four variables involved in this: two numerical, body mass and flipper length, and two categorical or factor variables, species and island. And this can be easily handled by mapping the numerical variables to the x and y axes and using geom point to create scatter plots, but then mapping the categorical variables to other aesthetics. So let's map the flipper length to the x-axis. We will map body mass g to the y-axis, and then we can map the color species to the color, and we can map island to the shape, and we can then add the geom point geom. When we run this code chunk, we can see a scatter plot between flipper length and body mass, but color indicating species and the shape, circles being bisco, triangles being dream, and squares being Torgens and islands. Now, although it's possible to do this, it's a little bit harder to interpret this plot because there's too much going on in order to be able to interpret this easily. So ggplot provides a way of having multiple plots where you vary the value of a categorical variable in each plot, and this is known as faceting. So, like before, we will map x to flipper length body mass g will be mapped to the y-axis, and we will map species to color. We will have geom point as before, and on top of that, we will use this function called facet wrap, and we will tell facet wrap so that each plot, each facet should have one value of the categorical variable island. And this is done by using the tilde symbol over here to tell the faceting function to vary the value of the island categorical variable with each facet. And when I run this code chunk, I get a scatter plot where I have three facets, one for the distributions on Bisco, another one for the distributions on Dream, and the third one for Torgerson. And this is a little bit less busy than the previous plot and a little bit easier to interpret. Finally, let's talk about how one can save plots to an image file. So far, we have just been displaying plots in the notebook, but sometimes you may want to share your results either in publications or you may want to make a presentation, and so it's sometimes useful to save the plot in an image file. And so what we're going to do is we're going to save this plot and give it a name, first name dot last name hyphen save plot one dot png, and we'll save it in the submissions module one subdirectory. And that can be easily done by running the ggsave function, and it takes an argument called file name, which specifies the file name. And the file name should be in quotes because it's string data, it's a literal string. And we're going to simply say manu. In my case, that's the first and last names, first name dot last name hyphen saved plot one dot png. And this ggsave should be in the same code chunk in which you are running ggplot, and we can run this code chunk, and this has saved the image. And if you want to see the image, we can go back to files tab of the output pane and navigating to submissions module one, and you can see there's a png file, and I can click on it to open that file. And you should, in order to submit it, follow the instructions for adding this file to the repository and committing it and pushing your changes.